Hi guys, this is Miss Gray, and this is the last podcast that we're going to do about electrons and electron configuration. So I want to make sure that we can get this right. We're going to put it all together, and then we're going to talk about the exceptions to the rules. Once you've learned all the rules, it's important that you also learn the exceptions. So here's our basic strategy. We're going to use the electron configuration that we just learned how to do to help us draw the Bohr diagrams and the Aufbau diagrams. And in order for us to accomplish that, we're going to use the periodic table. We're going to go from top to bottom and left to right until we get to the element that we're interested in. So that's our strategy. Let's give it a try. First, we're going to work with elements that are in the S and P blocks because those tend to be the simplest ones. So here's what I want you to do with your periodic table. I actually want you to fold it across. Okay, here we go. 4 and 5 are touching each other now. So bring your P block across so that it's in contact with your S block. So here's our P block, and then this one here is our S block. All right, you with me so far? Now let's work on a diagram for something in one of these blocks. Let me clear some space so we can see what we're doing. Let's work on the electron configuration for carbon. So to get this done, we're going to start on our periodic table going from top to bottom, left to right. So our first thing is hydrogen. It's in the S block, and so is helium. There's only one orbital we can have in energy level 1, and that is the 1s. And it holds at the most 2 electrons. So now that we're done with helium, we're going to move on to the next row, row 2. So after 1s2 comes the 2s, because this is our S block and this is our P block. So in the 2s, I can hold at most 2 electrons. And now, since I folded my periodic table over, it's pretty clear what comes after my S block is my P block, right? Because this section right here is the P block. I'm still in row 2, so it's 2p. And to get from this end all the way to carbon, you know, from left to right, I have 2 steps to go. So it's 2p2. In shorthand, we could write helium and then 2s2 and 2p2. But that doesn't seem to save us a lot to use a shortcut for something as small as carbon. Alright, well now that we've got the electron configuration, this will help us to draw the Bohr diagram for carbon. So carbon is number 6 on the periodic table. That means it has 6 protons. Then we subtract mass number minus atomic number to find 6 neutrons there. And then we know since we're in the second row, we need 2 rings. 1, 2. And this tells me how many to put in each of them. In the first ring, I get a total of 2 electrons. In the second ring, here's my 2s. I'm going to add these up for a total of 4 electrons. So there's the Bohr diagram for carbon. Now let's do the Aufbau diagram. We're going to start with 1s and put an up arrow and a down arrow because we have to be opposite in spin. After the 1s is done comes the 2s. We need 2 arrows in that one. One goes up and one goes down. And then when we do the 2p, remember we're going to put 1 in every space before we start pairing them up. So for carbon it's going to be 1 here and 1 here, and we're done because we only need 2 electrons in that 2p orbital. So that's it. That's how we use the electron configuration to help us draw the Bohr diagram and the Aufbau diagram for elements in the S and P block. So let's take on a challenge. How about elements that are in the D block? Here's our D block in the middle. If you have elements in the D block, then we're still going to be going from top to bottom and left to right until we land on the element that you're interested in. So let's pick something we haven't done before. How about platinum? Nope, that's going to be in the F block too. Let's do palladium right above it. Palladium has 46 electrons. We're going to find the home for each of them, draw a Bohr diagram, and then draw Aufbau diagram. So we better get started because this could take some time. Don't worry, I'm a trained professional. We're going to start with hydrogen up top, and we're going to fill in that s orbital, right? So I'm going to fold my periodic table back together until I get to where the numbers don't line up anymore. So steps 1 and 2, right here, are filling in the s block in the 1s. Put 2 electrons there, and we're down to the second row. So I get my 2s with 2 electrons, and then now we're in the p block, so I go to 2p. Fill it all the way up. Now we're down to my third row, and here's my s block completely full, so I put 3s2, and it's pretty clear what comes after 12? 13. So I'm in the p block now, and we're going to fill that all the way up, all the way across to argon, and that puts us in the fourth row now. So 4s, fill it up, and now my numbers don't match. So what do I need to do to get my numbers to match? Let's put the D block back in. Alright, so unfold your periodic table. We've got to have our numbers going in order, 20 and then 21. So after number 20, the 4s is full. Now we're in the D block. So we're going to have to write a d orbital, but it's not 4d. D block is always energy level -1, n -1. So instead of writing a 4, we're going to put a 3 there. Count across until you get to the end of the D block, because we're still not even in the row for palladium. 5, 6, 7, 8, 9, 10. Now some of you smarties already knew there's 10 electrons in the D block. That's alright. But look, what comes after 30 is 31, and now we're back into the P block. And P block is normal energy levels. So we were in 4s, we're going to be in 4p now. And I ran out of space here. So 4p gets all the way full up to 6 electrons. Next comes the 5s. Right? Once we get to the end of the P block, we're down to the next row. So 5s gets 2, and after 38 comes 39, so we're back into the D block. Let's count across till we land on palladium. 6, 7, 8. So it's going to take us 8 steps. Remember, the D block is n -1, so here I had 5. Now I need 4d, comes after 5s. And that's going to be 8 electrons, because it takes 8 steps to get to palladium. So there's our configuration. How do we use this to sketch the Bohr diagram? I wish I had my eraser, but I don't. So what we'll do now is the Bohr diagram. Palladium was, I gotta see what number again, 46, right. So for palladium, we're gonna have 46 protons. And let's look again at the mass number, 106 minus 46. Well, that's 60, right? 60 neutrons. And then I need to draw 5 rings because I'm in the 5th row. So there's 1, 2, 3, 4, 5. If you don't really look so much like rings as they look like stripes, but that's okay. This is our shortcut method for the Bohr diagram. Alright, let's look and see where's my first ring of electrons would be. Anything with a 1 in front of it, so I can only put 2 electrons there. 2 in the first. That's as much as it will hold, right? Now let's look at the second. So 2 and 6 adds up to 8. That's as much as the second ring level will hold. And now we're up to 3. So I have the 3s and the 3p. And I also have this guy over here, the 3d. So let's not forget him. So let's see, we have 2 plus 6 is 8, plus 10 more makes 18. Great. Now we're moving on to the 4th row, 4th level, 4th ring, 4s and 4p and 4 D. So how many is that altogether? 2 plus 6 is 8, and then 8 more is 16 in the 4th ring. And finally, we'll wrap it up here in our 5th ring, 5s2. So in the outside ring, we have only 2 electrons. So that's the Bohr diagram for palladium. Now let's draw an Aufbau diagram. See if I can squish it in here. So we're going to do up and down in the 1s, and then the 2s, and then the 2p. Fill it up. After 2p comes 3s, and then 3p, after the 3p we went to 4s, so I'm just going in the same order as your configuration here. And after 4s, what did we do? 3d, right? So the d needs its own set. Over here, 1, 2, 3, 4, 5, gotta have 5. So 3d is all the way full. And after 3d, what did we do next? 4p was next, so follow your configuration and you'll get this right every time. That's why you've got to write the longhand configuration if you're going to use it to help you with the Aufbau diagram. Okay, after 4p, then we had 5s. Alright, 5s. Make sure that you're lining all your s's up together and all your p's in the same row. Then our d's have to go in the same row, and I don't have any more space to show my 4d. That's inconvenient. So we need 5 spaces. I'm just going to scroll over the top of this. Sorry for the confusion. 1, 2, 3, 4, 5 spaces. 4d has 8 electrons, so we're going to put 1 in each. There's 5 spaces, and now we can start pairing them up. There's 6, 7, and 8. So, sorry that it looks kind of sloppy, but you get the idea. Use your electron configuration to help you sketch out the Bohr diagram and the Aufbau diagram. Now that we've done something in the D block, let's go on to something bigger. There's also elements in the F block. Yeah, so here's what I need you to do. If you haven't already made a periodic table where you put the F block back where it belongs, then I need you to cut it apart and put your numbers in order so that your 56 and your 57 lie side by side. So take the part that's on the bottom and tape it back up into your periodic table where it belongs. We want our numbers to go in order so that we can do these diagrams and use the shortcut method and the longhand configuration and all that good stuff. Alright, well, let's pick something in the F block. I gotta see that bad boy again. Let's just worry about samarium, because that guy's here pretty close. Here's samarium number 62. Alright, so we're going to write the electron configuration, and just like normal, we're going to start at the top and go from top to bottom, left to right, until we land on the thing that we want. So, you ready for this? Here we go. First of all, I want my numbers to go in order. So there's how I want it to be. Because when we first start out, our S block and our P block are getting filled up, right? So 1s2, and then 2s2, and then we're in 2p, 6, and then we go to the next row, 3s2, 3p6, and now we're on the next row already, 4s, and here's where we have to expand and get our D block back so that our numbers line up, right? 20 and then 21 has to come. So D block is 1 energy level lower, so that's 3D. And that's all the way full before we get to samarium. Come on back. Sorry, that's where I want to be. So then after the D block is full, that's at zinc, then comes the P block, 4P. 6 electrons can fit in there, and then we're down to row 5. And that's all the way full, 5s2. Back to the D block, 1 energy level lower puts us in 4D. So we've got 4D10. and then back to the P block, right? Here's the end of our 4D, and that puts us back in the P block, 5P. Our number goes back up because the electrons get too crowded in that P orbital to lower their energy. So after 5P, we're at xenon now. We've got to come down to 6. So in our 6th row, we're going to start out in the S, but then after number 56, we got to have number 57, right? And that's in the F block. Remember, F is 2 energy levels lower than the S. So we take n minus 2. 6 minus 2 is 4. So now we're in the 4F sublevel. We're going to count across until we land on samarium. So we go 1, 2, 3, 4, 5, 6 steps to samarium, 4F6. So there's the longhand configuration for samarium. Now let's draw a Bohr diagram for this. How many protons? Check out the atomic number. Got to be 62. And now we're going to take our mass number that's rounded to the nearest atomic number, to the nearest whole number, 150.4 rounds to 150, and subtract 62 protons for a total of 88 neutrons. Now we're in the 6th row down, so we're going to need 6 rings. 1, 2, 3, 4, 5, 6. Let's use our electron configuration to do the Aufbau. 1s gets 2 electrons, so I put a 2 in my first ring. And then in my second ring, I have 2s and 2p for a total of 8 electrons, just as usual, right? Then in the third level, I have 3s, 3p, and 3d. So I've got to add those all together for a total of 18. All right, then let's go on to the fourth ring. 4s, 4p, 4d, and 4f. There's all my 4s, right? So let's add these together. 2 and 6 is 8. Then 10 more is 18. And then 6 more, that's 18 and 6. 24 electrons go in my 4th ring. So we're cruising now. Let's take our 5th row, 5s and 5p, and that's it for the 5s. So I just have 8 in my 5th ring. Then my 6th ring has the least. 6th ring has only 2. And we're done. There's the Bohr diagram. Alright, well now what do we do for the Aufbau diagram? Let's start down here. Hopefully I'll not run out of space. So my 1s gets full, and then my 2s gets full. Then we go to 2p and fill that one up with all your arrows up and down, and move on to the 3s, then 3p. So I'm going in order of my longhand configuration from left to right, just filling everything in order. Now once you get the Aufbau structures and you know what order to put these things in, you could use the shorthand configuration to help you draw this. You just have to know what it's going to do, you know what the pattern is. Alright, so then 4s, after 4s comes 3d. So we need 5 spaces for the 3d because there are 5 shapes of d orbitals that we could possibly have. Fill that all the way up, 3d's full, then we go back to the 4p and fill that guy up. Now we're on to 5s. That's all the way full. After 5s comes 4d. Think we're going to be able to fit this whole Aufbau diagram in this little space? I'm doing my best here. After 4d comes 5p. Fill that up. And then 6s. Finally, we're in the row of samarium. And now the f orbital comes next, right? After 6s comes 4F. So we need to have a space that's just for the F. 1, 2, 3, 4, 5, 6, 7 different shapes are available in the 4F sublevel. And we need to fill in 6 electrons here. So I'm going to put 1 in each space before I start pairing them up. So I can only fill in that many, right? There's only 6 electrons, and so I'm not going to get to pair up any of these. This is Hund's rule. Every electron that fills in first is going to fill in with maximizing the spin number. They're all going to spin the same direction before we start pairing them up. So that's it. There's our Bohr diagram and our Aufbau diagram for something in the F block. I hope that this has been helpful. Get your periodic table and use it. Fold it up and unfold it until you get to the element that you need. Make sure that you put them in order so that you can count the numbers in the order that they really go, and you'll be all set. All right, last thing. I've got a question for you. Well, now those are the normal rules, but I want to show you the exceptions to the rule. I told you there would be some, so now let's figure out what they are. The exceptions to the rules would be elements for whom the regular configuration just is not the best situation. So let's look at chromium. Get my pen. Chromium here is number 24, and it's in the D block. Our exceptions are always going to exist in the D block and in the F block, but the ones that I really want you to know about are the chromium family and the copper family. So I'm going to write this electron configuration for chromium. 1s2, 2s2, 2p6, then we're at 3s2, 3p6, 4s2, and now we're in the chromium section, right? So we have 1, 2, 3, 4 electrons here. Now you'll see this best if I show you the Aufbau diagram for chromium, and then you'll see why it acts like a weirdo. So give me some space for an Aufbau diagram. Wow, that was crooked. There's our 1s, and we get 2 electrons there, then 2s, and then we fill in the 2p, 3s, 3p, and then the 4s, and then our most critical one, 3d. So electrons go where they go, all because of stability. The most stable configuration is the one that's going to win out. The one that requires the least amount of energy is the one that's going to be the most stable. So you'll notice here that there's an empty space in the D block. And a half-filled orbital would be more stable than this guy, where we're just 1 electron short of being half full. So instead of having this configuration with this empty space, chromium's going to take 1 out of the s and kick it across to the d orbital. It gets promoted to the next level because then it is more stable. So doing this improves its stability. So rather than having 4s2, 3d4, the real configuration for chromium is 4s1, 3d5. So that's why I call chromium a weirdo, because it doesn't follow the rules. It kind of makes up its own rules. But chromium's not the only one that does this. See, all of these guys in the chromium family, molybdenum, tungsten, and seaborgium, they all do the same thing because their outside energy levels will be similar to chromium. So if this were molybdenum, then we would just keep going and filling this up all the way until we get to 4D. 5 things in the 4D, and then molybdenum would look like this. It would have 4 electrons in the 4D. So of course we've got 5p and 5s filled up. Oops, first 4p, then 5s, and then 4d. So we fill up all these electrons, and then we get to chromium and have 4 electrons. Well, to make it more stable, we're going to take one out of the s, put it in the d over here. And of course, I'm going to take the one that's spinning up because I have all the rest of mine in the 4D spinning up. So I have to match them all, maximize my spin. But this whole entire family in the D block chromium is going to be a weirdo. Kick one out of the S and move it to the D. There's another family that you need to know about that's going to do the same thing, and it is the copper family. So copper, silver, and gold, and whatever this UUU thing is now down here, I think they've named it by now, but I don't know what its name is. So the copper family is also going to take one electron, move it out of the S block, and move it to the D. Let me show you the Aufbau diagram so you can see why that improves the stability for the copper family. So let's clear that out of the way. So copper is, let's get this back. Copper is 1s2, 2s2, 2p6, then 3s2, 3p6, 4s2, 3d. Let's count across 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, now let's talk about stability. Draw for copper. We'd fill in everything up to the 4s, and then in the 3d put 9 arrows for the 9 electrons. But we could improve the stability of this configuration if we could just put one more electron here. So we're going to take the down spinning electron this time from the s orbital and promote it to the 3d. This lowers its energy from a 4 to a 3 so that it gains stability by moving. And so it takes energy to get it to go into the 3D, but we gain that energy back and then some by improving the stability of that electron. So the copper family does this, not just copper, but everyone in the copper family, which would include silver and gold. That's why copper, silver, and gold tend to be less reactive than other metals, and we use that to our advantage, right, when we make jewelry and stuff out of those things. And they tend to have similar properties too. So we make jewelry out of copper and silver and gold, and we use them for lots of different applications. Those are the exceptions you need to know about the chromium family, the whole entire family, and the copper family, so that you can get those electron configurations right. Oh, so yep, we got to kick one out of the S and move it to the D. So now our configuration is 4s1, 3d10. So be careful when you meet up the exceptions. In the F block, you'll have exceptions for similar reasons. Whenever you get a half-filled orbital at an F6, remember half-filled would be F7, right? So we'd promote one from the S to the F, but I don't expect you to know which ones are exceptions in the F block, just the D block for chromium and copper. Alrighty, that's it. So I'll see you guys later. So here's your homework question. Question number 1, that is, because I have another one for you. In order to occupy the same orbital, 2 electrons must have, what do you think, a high quantum number, the opposite direction of spin, low energy, or the same direction of spin? This is especially important when you're drawing an Aufbau diagram. So there's your hint. To answer this question with a text message, remember regular text messaging charges apply. So if you don't have unlimited text messaging, it's going to charge you for sending this text message. You can also go online and submit your code at this website, the http polev.com. All right, good luck with that question. Let me show you another one. Your next question is, where is it? How do I get it? Okay, here's your next question that I need you to send your answer to me. According to the quantum mechanical model of the atom, electrons are found where? In orbits around the nucleus of the atom in exact locations? Or is it in exact locations in SPD and F orbitals? Or would it be attached to the positively charged matter of the atom? Or your last choice is in various energy levels with a 90% probability of their location. What do you think best fits the quantum mechanical model proposed by Erwin Schrödinger? So send your answer to poleeverywhere.com, either using that text message or by submitting your code on this website. Good luck with these questions, and I'll see you soon in class.